Look at acid-base neutralization and titration reactions. This is a combination of two things. When we learn how to write reactions back in first semester, this is going to be a double replacement kind of reaction when we're predicting the products. And then when we're working on the calculations, it's actually like our solution stoichiometry chapter that we just did. So I'm going to start with this worksheet that we have. What type of reaction is a neutralization reaction? A neutralization reaction ends up being a double replacement reaction. We're going to have two compounds and they replace. The generic equation for a neutralization reaction, we're looking at acids and bases, but we're only going to look at strong acids with strong bases. So we've got our strong acid plus our strong base, and they make water and a salt. Salt is a generic word for an ionic compound. This will be soluble in water. And so this right here is the actual, if we were only writing a net ionic equation, this would be what it actually makes. I have, now that we are farther ahead in chemistry, I have kind of shortcuts for this. In a double replacement, I always taught you to circle around, put the outers together, and then do the inners back like this. So H and OH are going to go together. This actually makes water, but I'm going to write it like that because it's easier to balance. And then Na and Cl go together. You got to pay attention to charges. So the H forms a +1, OH, that's a hydroxide ion's a minus, so +1 and -1, they go together. They don't need any subscripts. And then sodium always forms a +1 charge and chlorine a -1 charge. So they also go together 1 and 1. I can figure out their charges also by looking at the compounds. I know that hydrogen's a 1, so if these guys are together 1 to 1, that must be a -1. Same thing here, since this is a -1, then that must be a 1. So this is actually balanced like this. You might want to go back and rewrite that as water. So it's 1, 1, 1, 1. No balancing needed. If I go down to letter C, I've got 2 OHs and 2 Hs. That means I'm going to end up having a coefficient. Same thing, outers go together, back to your inners. The Ca and the SO4. Since this is a 2, that means this must have had a -2 charge. Since this is a 2, that means that must have been a +2 charge. That one's in the second column of the periodic table, and they always form a +2 charge, the alkaline metals. SO4, if I was to look it up on an old polyatomic ion list, I would see that it also forms a -2. The 2 and the 2 cancel out, so they don't need a subscript. Plus, H and OH go together. It's not going to be H2OH2. It's making water. How many waters? Well, 2 of those and 2 of those will end up making 2 waters. And actually, now it's balanced. I can usually scan and see that. See, 2 of those and 2 of those. That's also going to make 2 waters. Down here at the bottom, this one's got 3 of these and 1 of these. So watch how I do that. So the Al must have a +3 charge, which aluminum does form that. It's one of the ones that doesn't change. Since there's only 1 in 1 of these, remember that 4 is part of the polyatomic ion. That one must have a -1 charge. So when I put aluminum with a +3 charge with the ClO4 with a -1 charge, I'm going to have to crisscross and reduce on that one. My 1 goes there, and then the 3 is going to go here. I want to make sure it doesn't look like 43, so I have to put the polyatomic ion in parentheses. Don't leave any little charges in these reactions. These are not the ionic reactions. They're not complete ionic or nor net ionic, so I want to just get rid of those. H and OH are going to make water. I already know that since there's 3 of those, I'm going to need 3 H's to balance it out. And look, see, I need 3 ClO4s, 3 ClO4s, 3 H's, 3 H's, 3 of those, 3 of those. They make 3 of those. Make sure I don't have any of these charges in my final balanced equation. And bam. Watch out for this one with the 2 and 3. That one will be tricky. Can you get that one? Okay, down here at the bottom, we've got some neutralization reactions. I'm personally going to need more paper. You're going to need to write the balanced chemical equation first. A lot of them are going to be up top. So if you have that top part done, you can do this. But I'm just going to, actually I did do this one. This is letter C. This and this, 2 and 2, so CaSO4 plus 2 waters. So now I'm balanced. Go through and double check and add them up if you need to. Make sure you're balanced. And then I'll write what they give me. What volume of the H2SO4, so I'm looking for volume, 2 molar, will be required to neutralize 54.1 milliliters of 1.40 molar. Looking familiar? This is solution stoichiometry again. But what's really nice about these, really, they don't ever throw in grams. So I'm going to start here. You can convert that to liters and that to liters if you need to, but I'm not going to do that anymore. I'm going to show you what we do in AP chemistry. Molarity is moles over liters. Molarity is also millimoles over milliliters. So instead of dividing by 1,000 and then multiplying by 1,000 in the same problem, I just multiply these two numbers in my calculator. Oh, sorry, let me show you. I'm going to take my milliliters, I'm going to bring it up, I'm going to cross multiply it by my molarity, and what am I going to get? Millimoles. So the millimoles that I have is going to be molarity times milliliters. This recipe, even though I've always like it's the mole recipe, I can also say that it's millimole to millimole. So 54.1 times 1.40, 75.74 millimoles of my CaOH2. Now that I have millimoles of that, I'm ready to use my recipe. It's a 1-to-1 mole ratio. You got to at least write the 1-to-1 for me. Millimoles of the CaOH2 to 1 millimole of the H2SO4. Same number. Now I've switched it to the H2SO4. Then I'm going to use the molarity equation. So that's the first step. Second step's mole to mole. Third step, back to the molarity equation. Molarity is millimoles over milliliters. So I'll plug in my 2 there. 75.74 millimoles there. Looking for that. Bring that up, bring the 2 down. Divide it by 2 in my calculator. 37.87 milliliters. Oh, they run. Oh, yeah, 3 sig figs. Let's look at number 6. It was found that a triprotic acid was needed for this. Okay, being a little tricky here. I have a triprotic acid. What does that mean? H is my proton. I have tri of them, 3. Well, what's the rest of it? You know what? Doesn't even matter. In fact, a lot of times acids, they call them HA. A stands for the anion that it's with, whatever negatively charged particle. So I'm going to take that, add my NaOH to it. I need to figure out what's over here so I can balance it. I mean, I do know that if I have 3 here, I'm going to need 3 OHs to go with it. So if I wanted to stop at that point, that's really all I need in this problem. Because it says I have 33.8 milliliters of this. What's the molarity of it? What is the molarity of the acid? If it neutralized 43.1 milliliters of 1.10 molar. Sorry, I was cut off. So I only need these 2, but say you hadn't recognized that at first, and so you want to know how to finish writing this because you're kind of confused about what goes with what. So the Na is going to go with the A. Then you're like, well, how do I know what things to go here? Well, triprotic acid, this 3 means that this guy must have been a -3 charge. So I got a -3 charge, a +1, so it's going to be Na3A. Or I guess if you needed to, just put something in there that had it. Like you could try to do nitrogen or something that has a -3 charge. When I'm balancing, I like to write water as HOH with acid-base neutralizations, so then I can see where they come from. So I have 3 H's, I'm going to need 3 H's. I have 3 OH's, I'm going to need 3 OH's. 3 NA's, 1 A, 1 A. Done. So the math here, watch out, we have a 3-to-1 mole-to-mole ratio. Going to multiply those. I have 47.41 millimoles of my NaOH times mole-to-mole ratio. Okay, I've got a 3 in there, top or bottom. It's going to go on the bottom to 1 millimole of the H3A. Divide that by 3. 15.8 millimoles of the H3A. And then you take your millimoles, divide it by those milliliters, and that'll give you your molarity. Done. Okay, you try some more of these. And, oh, some more of these. You're going to need to write those reactions out. Watch out, this one does throw in some milligrams. Let's see if you remember how to do that from the last one, just so that you know the milli, you will need to divide this one by 1,000 to put it into grams because your molar mass is in grams.